When an inductor is connected in series with a capacitor and the two are driven by a sinusoidal AC source, the net impedance in the circuit is the vector sum of the inductive reactance and the capacitive reactance. These three quantities can be represented as vectors in a phasor diagram. From complex numbers, it follows that capacitive reactance is phase shifted from the reference line by negative 90 degrees, while inductive reactance is phase shifted by positive 90 degrees. So, the impedance, which is a vector sum of these two, can be net inductive or net capacitive. This impedance produces a phase shift in the current through the circuit. Whether the current leads or lags the supply voltage depends on whether the impedance is net inductive or net capacitive. Since both reactances depend on the frequency of the driving AC, we can alter their values by changing the frequency of the source. This results in a change in the circuit impedance. At very low frequencies, capacitive reactance is generally larger than inductive reactance, resulting in a net capacitive impedance. This means that current leads the source voltage by 90 degrees. As the frequency of the source is increased, inductive reactance increases while capacitive reactance decreases. This means that there is a particular frequency at which the two are equal in magnitudes. Since their vectors point in opposite directions, the vector sum is zero. This means that the effects of inductive reactance and capacitive reactance neutralize each other, and the net impedance is zero. From Ohm's law, it follows that the current flowing through the circuit is infinity and is in phase with the supply voltage. This phenomenon is known as resonance, and the frequency at which this occurs is known as the resonant frequency. If the frequency is increased beyond this resonance point, the inductive reactance becomes larger than the capacitive reactance, resulting in a growing net inductive impedance. So, as the frequency is increased further, impedance increases and thus the current decreases and is now lagging the supply voltage by 90 degrees. In practice, inductors generally have a more significant resistance than capacitors due to the length of conductor used in their construction. This means that the LC circuit we have been discussing is really an RLC circuit, with R being the internal resistance of the inductor. This changes the behavior of our circuit in a few ways. We now have a resistance which produces no phase shift in current, meaning that the impedance of our circuit is now given by this formula. This impedance will produce a phase shift in the current whose magnitude is between negative 90 and positive 90 degrees, depending on the vector sum of the two reactances, and at resonance, these two cancel out, and the net impedance is R, which is its minimum value, and it produces no phase shift between the current and source voltage. So, at resonance, the current no longer goes to infinity, but reaches its maximum value, given by Ohm's law. This is the general profile of the current as a function of frequency. When frequency is zero, no current flows. This makes sense because at zero frequency, the voltage is not oscillating, meaning that the supply is actually DC, and as we know, capacitors block direct current. As the frequency increases, capacitive reactance decreases, while inductive reactance increases, meaning that the net impedance decreases until it reaches a minimum at resonance. This means current increases and reaches its maximum at resonance. As frequency increases beyond the resonant frequency, the inductive reactance grows further, while capacitive reactance shrinks, meaning that the net impedance starts to increase again, and current falls. As frequency approaches infinity, the current decreases to zero. This is because infinite frequency implies an ever-changing current, and thus the inductor will offer an infinite opposition to current flow. The rate at which current rises and falls in this profile depends on the relative magnitudes between the reactances and the resistance. If the reactances are of comparable sizes to the resistance, the current rises and falls gradually. This is called a broad resonance curve. On the other hand, if the reactances are large compared to the resistance, the current rises and falls very rapidly, and this is called a sharp resonance curve. A circuit with a sharp resonance curve is said to have good selectivity. meaning that the current amplitude responds strongly to the resonant frequency alone and discriminates against others. A circuit with a broad curve is used in situations where a good response over a band of frequencies is desired. Sharpness of a resonance curve can also be expressed in terms of a quantity known as quality factor. It is defined as the ratio of energy stored, represented by reactance, to the energy lost by a device, represented by resistance. For an RLC circuit, the major contributor of resistance is the inductor, so the quality factor of an RLC circuit is solely determined by the inductor. Since there is no load connected to the resonance circuit, this quality factor is called the unloaded quality factor. High quality factor implies a larger reactance to resistance ratio, meaning that the resonance curve is sharp. A low quality factor means that the resonance curve is broad. An alternative way of expressing the sharpness of a resonance curve is via bandwidth. This is defined as the range of frequencies over which the current is greater or equal to I max over root 2. Since power is proportional to I squared, the endpoints of this spectrum yield half of the power at resonance. By converting this to decibels, we can also call this point the -3 decibel point. Bandwidth is often calculated using this formula. So, a higher bandwidth implies a broader resonance curve and vice versa. That's it for the basics of series resonance circuits. Thank you for watching.